Yeah, so, yeah.
Since I missed last class because my emergency, I didn't get a handout like in the video you mentioned the handout.
Oh, well, I don't have any more new ones, so. The handouts are on my website though, so you can print it out
okay.
yourself.
Okay.
Is your
Whoever
hand,
needs
did your hand
handouts.
explode?
No, it's actually gotten better.
Wow, amazing.
Yeah. It like swole up and now it's back.
So we're not gonna get to these today, but I already printed them, so you guys just have to keep them till we get back. Yeah.
Oh no. I remember these.
You remember related
Oh my
rates?
god, these.
Oh dear. Oh dear.
It's not so bad. Be quiet. Stop exaggerating, you guys.
Oh no.
It's just
This might be the worst.
Related rates.
actually the worst.
It wasn't that bad, just
Okay, we will.
You remember optimization?
Yeah,
Where we get to
it's-
optimization?
Oh, optimization was like alright.
Yeah,
Yeah.
no, I got it.
Related
Come on.
Did you really put pun in on the first paragraph?
No.
Yes, you did.
Okay, so we're gonna start. We're gonna do exponential growth and decay. So get your stuff out for that. So I believe that's 3.6.
Yeah.
So we're just going to run through this. It shouldn't take very long because the set of formulas that we have, I'm not really going to derive them because we need like integration to derive them and we haven't done that yet. So at this point it's sort of you memorizing the formulas and just applying them as needed. So that's pretty much exactly what it's going to be like. So that's what we're going to cover now. We're going to cover exponential growth and decay. And basically this happens when a quantity grows or decays. Right, so grows implies it's increasing in size. Decay implies it's decreasing in size. And it grows at a rate proportional to its current size. So that would distinguish it from linear growth, which we know grows at a constant rate per unit time regardless. So if it always increases by the same absolute value, it always increases by 2 per unit time, that gives you linear growth. But if it increases by 2% of its current size per unit time, that gives exponential growth. So it grows proportionally to what it currently is. And you get two sets of formulas from this. So we can talk about the growth set of formulas, which are very similar to the decay set of formulas. So this means the rate of growth, which we know can be conceptualized by the derivative, is proportional by, we call the constant of proportionality R, to its current size. Now you can solve this using integration and a simple application of differential equations to end up with the fact that P is equal to P naught e to the RT. Whereas you can see in the list of formulas there, P is the current amount at time t. P naught refers to the initial amount that you started with at time equals 0 whenever you started the clock. R is going to be called the relative growth rate or the growth constant, and that's just basically the percentage value that something is growing at in decimal form. So if you know it's growing at 5%, then it's 0.05 is what you're plugging for R. T represents time, and E is of course the usual Euler's number, E. You can also get the fact that the time to double is going to be ln2 over R. That means if you start with some mass now, how long will it take for that amount to double if it's undergoing exponential growth? That will be the amount of time. Decay is very similar, except you have a negative rate because it's decreasing. And when you solve that, you get P naught e to the minus RT. And in this case, you have what we call the half-life, which I would represent by T sub h. This is also ln2 over r. Because r itself is always considered to be positive, we put the negative in here, and so that's how you get that. We can actually derive these formulas. That won't be so bad. We actually know how to do that at this point. So let's quickly do that. How about time to double? So let's say we have p is equal to p naught e to the rt. How you can figure out the time to double, and this is very instructive for other kinds of problems as well. But we want t so that the current amount is double what you started with. So this means you have 2p naught equals p naught e to the rt. You can divide both sides by p naught. So you get 2 is equal to e to the rt. I want to solve for time, the time to double. How do I solve for time? Yeah?
Take the ln both sides.
You can use logs to get rid of exponentials. So this gives us that ln2 is equal to rt, and therefore we end up with time is equal to ln2 over r. And that's the time to double. We call that t subscript d. And the thing special about the 2 is that that tells me I'm double. If I wanted the time to triple, that would be ln3 over r. Time to quadruple, ln4 over r, etc. And so that's how we would get that. If you look at the half-life, when something is decaying, relative to its current size, half-life is the time taken to have half of what you started with. Right. For those of you who did chemistry, half-life would be something that you hear about all the time. So this is when you're decaying, and you want to figure out after how long will I have half of what I had before. And so this means we're looking at p naught e to the minus rt, and we can set this guy equals half of what we had before. Again, divide both sides by p naught. We can ln both sides. This guy would cancel. So we have ln of 1/2 equal to minus rt, which means that your t is equal to ln of 1/2 over minus r. And I claim that's the same as ln2 over r. How would I get to ln2 over r from that? In the formulas I said half-life is equal to ln2 over r. Here I have ln half over minus r. How can I simplify that? How could I rewrite ln of 1/2 for example? What's that equal to? ln of 1/2.
ln of 1 minus ln of 2.
I can break that down to ln of 1 minus ln of 2. What's ln of 1? What's ln of 1? 0. Log of 1 is always 0, no matter what's the base. So this becomes minus ln2 over minus r. The negatives cancel, so you get ln2 over r. So it turns out the half-life is ln2 over r, and the time to double is ln2 over r. They both are the same equations. The difference between growth and decay is pretty much that negative power, but everything else is pretty much the same. The behavior is the same, they just move in opposite directions. One increases while the other decreases. So it might be a bit obvious, but let's just be comprehensive here. When would you use these formulas? So there are certain kind of buzzwords that hints to you that you have to use the set of formulas that I gave you in this handout. For one, you see phrases mentioned like proportional to current size. You can also see things like radioactive. You can also see things like compounded continuously. See things like half-life. So whenever you're seeing any of these sorts of phrases, it means you're looking at exponential growth and decay. In terms of compounding continuously, that means exponential growth. Half-life would refer to exponential decay. Radioactive would refer to exponential decay. This can refer to either one, it depends on the situation. So that's how you would know that you use them. Once you see any of those buzzwords, you know that you're looking at this sort of problem. Also, some terminology is important here. So that's something else you'd have to pay attention to. If you see things like relative growth rate, or you see things like growth constant, right, okay, phrases like that refer to the little r in your formulas. So if you see those words, it's referring to little r. If you see just, it's a bit confusing because they both have growth in the name, but if you see growth rate or rate of growth or rate of change or something similar, this is referring to p prime in your formulas. If you see something like differential equation, that refers to the equation p prime equals r p or minus rp, depending on the situation. You might see some like initial condition. And that refers to that equation that says at time equals 0 you have this amount. So this is some constant you can find, but it refers to that equation. So this would hint you when you want to use these sets of equations, and these words are referring to particular things. If you talk about, if it says something like find the current amount, or find P of t or something similar, that's of course referring to the general formula P equals P naught e to the RT. PERT formula, you know, like the shampoo PERT. I don't know if you guys remember that. That came out when I was a kid. First shampoo that had shampoo and conditioner and water. Like, oh my god! What is this technology? I'll save so much time. Okay. Yeah, everything was exciting back then. It's like, what? You got Windows DOS? That's amazing. I wish I had Windows DOS. What? Your floppy disk holds how many megabytes? You have a 25 megabyte hard drive? That's amazing! Oh, yeah. Well, yeah, we had, that's how I remember it, the PERT formula, that's what I call it.
Shampoo and floppy disks. What a time.
We're living in the future.
Yes.
We were the future, yeah. It's like, how's it conditioning your hair and shampooing it? Like, what? You know, and then you had all those people, it can't be good for your health, and You know, those same people who are like, energy drinks will kill you, those people, they were back with the whole shampoo saying, it can't be, it's unnatural, it's not natural. Okay. Okay, so that's kind of how these things work out. Those are the hints that you need to use this, and those phrases refer specifically to this. So let's actually just do some examples. If you look on the opposite page, look at example 1. And this isn't the relator, this is the exponential growth and decay handout, which I think, I gave that to you guys last time, so this is from last week. I forgot my own copy, so I'll just pull it up. So example 1. If you don't have the handout, you can also go to the class webpage. So Jhevon.org/teaching, you scroll to the bottom, you'll see the handout there. On the second page, you'll see the examples. We're going to just go through them, and then we get out of here. So let P of t be the current size of a population of a colony of bacteria at time t. At 10 a.m. there are 50 bacteria. At 3 p.m. there are 350. Assume the rate of growth is proportional to the current size. That sentence tells you you should be doing exponential growth, which means the formulas on the first page is what you should be using. And then we have the list of questions. Find the relative growth rate of the population. So we are going to do part A. It asks for the relative growth rate. Okay, what is that asking us for? T? No. T is time.
Is it R?
It's small r, it's little r. I don't think we have a big R, but it's little r. That's relative growth rate. So whenever you see that phrase, relative growth rate or growth constant, find that. They're talking about find little r. So how can we find little r? What information do we have? What do we know so far?
No starting bacteria, like the amount that we started with, and the
Yeah.
amount that we ended with.
So what's the amount that we started with? In other words, the initial amount.
50.
What symbol does that refer to?
Is that P naught?
P naught. So we actually know P naught is 50. We started out with 50 bacteria. What other information do we have?
PT.
Hmm?
We have PT.
Do we know PT? I don't think we know PT yet.
We know what the population is at 3 p.m. So.
Okay.
Yeah.
So we know something about 350 happens at 3 p.m. How would you express that as an equation?
P naught.
P of? Well, P naught is always the initial amount. It'll never mean anything else.
P of time?
Okay, how are you thinking of time? What would you say T refers to in this case? Well, one thing you'd want to do is choose units so that you can start to measure things properly. How do you measure them here?
In hours?
I measure them in hours. That seems to be the most straightforward one. So if it's not like painfully obvious, but you notice that you're being told at different times throughout the problem on the hour. Oh, this happens at 10 a.m. This happens at 4 p.m. What's happening at 6 p.m. or whatever, right? So it's talking about times on the hour. So I'll sort of use that T as measuring time in hours. And so what T value gives me this? 5. So T equals 0 refers to 10 a.m. So if I'm talking about at 3 p.m., that is 5 hours later, right? So I know these two pieces of information. How do I use that to get to the R value? How would I use that to get to the R value?
to use the PERT equation, so.
Use the PERT formula, so we know that P is equal to P naught e to the RT, and so what do we know?
We know P naught.
We know P, so let's plug this in to be 350 equals P naught, that's 50.
We know T.
And we know that T, it's 350 at the point where T equals 5, so I can plug in T equals 5. And so R is my only unknown, I just have to solve this equation. How do I solve that equation for R? Divide both sides by 50. So that gives us 7 is equal to e to the 5R. ln, get rid of the e. So this means ln of 7 is equal to 5r, which means that my r is equal to ln of 7 over 5. It's okay to leave your answer like that, I don't care about the decimal equivalent. But I think that was 0.38 something, so it's roughly 39%. So we have bacteria that's growing at roughly 39% every hour. So that's your relative growth rate, that's part A. So let's look at part B. Find a formula for P of T. So again, when it says find P of T, what is it referring to? Well, the PERT formula. So we know that P is equal to P naught e to the RT. So I'm just going to plug in the values that we know. P is equal to P naught was 50. E, so the R I now know is ln of 7 over 5 times T. And so that's the answer. And you can leave the answer there. Notice here, E is the Euler's number, so you can't replace that. T represents time, that's your independent variable or your input. P is the output. So those guys you usually won't replace if they ask you for a formula. It's the P naught and the R. These are the constants that you need to plug in to come up with the general formula. But everything else stays as is for the general formula. And that's the general formula. That's finding P of T. So at any time T, I can find out the current amount by plugging in time into that equation. C, what is the population at, what is the size of the population at 4 p.m.? In other words, this is asking, what is P at 4 p.m.? How do you do that?
Can't you just plug in 6 at T?
Yeah, 4 p.m. means T equals 6. This just means P of 6. So it's 50 e to the ln of 7 over 5 times 6. And that's the answer. So these problems aren't that bad. One of the dangers that you run with these problems is it seeming way too easy. You know, you always have those students who are very suspicious. Is that all I have to do? That was way too easy. And then they erase it and then they come like 2 pages of some random stuff. No, it's that easy. There's nothing else to do here. All right, we found the formula. Just plug in a 6 right there. We're done. Just move on. D. What is the rate of growth at 4 p.m.? Rate of growth at 4 p.m. What is that referring to? P prime. So whenever you see the phrase rate of growth or growth rate, it refers to P prime. So this means we want P prime at 4 p.m. And we have a formula for P prime. P prime is equal to R times P, right? And P here is of course referring to the current time. R we already know, that was ln 7 over 5. And so we want, at 4 p.m. this is just P of 6. So I'll just plug it in. So the rate of growth at 4 p.m. is going to be ln 7 over 5 times the population at 6. This is 50 e to the ln of 7 over 5 times 6. And that's your answer. When will the population reach 1500? And what is this one asking you for? What are we being asked to find here?
When the population is.
Yeah, but what are we searching for? Which one are the symbols? Huh? T, time, right? Because it asks when. That's a time, right? So here we want T so that P is equal to 1500. So how do we do that? What formula do we use? What formula has P and T in it that I can take advantage of? The PERT formula has both. So I know that P is equal to, we actually have the formula, we had it in part B or something. 50 E to the ln of 7 over 5 times T. So I'm simply going to plug in 1500 here. So replace P with 1500 and I want to solve for time. So as we did before, it's very similar to what we've been doing. So you divide both sides by 50, so this side gets 30 is equal to e to the ln of 7 over 5t, and ln both sides. So you end up with ln of 30 equals ln of 7 over 5 times t. And so you end up with t is equal to ln of 30 over 7 over 5. Or t is equal to 5 ln 30 over ln 7. Remember, numbers inside ln's, you can't mess with them. So don't take that 5 and multiply the 30, you'd be wrong. Don't divide these numbers either, it has to stay like that. So that's the time. Now you could plug in your calculator and get a sort of decimal answer to that, but I wouldn't care. It's good enough for me. And that's problem 1. It wasn't so bad. Example 2. This is one that talks about half-life. A very common, well, these 3 types of problems are really the common types that you would ask in this section. So I can ask about exponential growth, usually be like a population or something growing like that. I can ask about something decaying, so I might mention a half-life, and compounded continuous. Compound interest. So in this one I'm asked about the half-life, so I know we're using exponential decay. The half-life of a radioactive substance is 30 years. Suppose we have a 200 milligram sample of the substance. Let P of T be the mass remaining after T years. Find a differential equation satisfied by P of T. What's the differential equation satisfied by P of T? What does the differential equation refer to?
P prime.
The P prime equation. So that's P prime equals?
RP.
No. We're decaying here, right? Because we have half-life, so it's decreasing.
Minus RP.
So minus RP. right? So when they ask for that equation, the thing is you need to find the R. How would I find R to be able to plug in and get the answer? What can I use to find R?
The 30 years and 200.
Okay, how would I use the 30 years?
Plug in. Would you use the PERT equation or no?
Could I use the PERT? P equals P naught e to the RT minus RT. What do we know?
You know time. No. Like,
What time do I know?
the half-life. The half-life, which is.
We know half-life. How do we use half-life?
Can you do the P equals ln2 over r?
That's what I use. I can't use this because at P naught, T is 0. That will kill my R. I can't use that. But there is an equation that uses half-life. The half-life equation is ln2 over R. That relates half-life to the R. I know that the half-life is 30. So T is, I'm measuring time in years, so 30 is equal to ln2 over R. This means that my R is going to be ln2 over 30. Which means the differential equation is P prime equals minus ln2 over 30 times P. Alright, so R and P naught are things you have to find and plug into these formulas. B. Find a formula for P of T. So what does P of T look like here? What is P of T? Huh? The PERT formula. Right? With the, of course, here because we're decaying, it's minus R. So I'm going to just plug those in. This is P is equal to, P is short for P of T. I don't always write it, but when I write P, I mean P of T. P naught is a constant. That is the initial amount, which here was 200 milligrams. E to the minus R. My R we found was ln2 over 30. Times T. So P of T. C. How much will remain after 75 years? How would I figure that out?
Just 75.
Just plug in T equals 75 and not. This is just asking it for P of 75. T is measured in years, so that's going to be 200 e to the minus ln2 over 30 times 75. You want it. After how many years will the mass be reduced to 1 milligram?
Would it be 1 on that side and then you try to find time?
Yeah. So you're asking for how long till P P equals 1? This is the question. So this means how long means you want time. And so what you do is you go over to the general formula, which I believe we did in part B. And so you plug in 1 on this side, 200 e to the minus ln 2 over 30 t. You want to solve that for time. Again, divide both sides by 200. You have this. ln both sides. So that ln of 1 over 200 equals this. So my t would be 1 over 200 divided by minus ln 2 of 30, so it's minus 30 ln 1 over 200 ln 2. Wait, is that okay? Can we have negative time? Is that negative or are we okay? Do you make a mistake or is that negative? Or would you get to this point in the test and be like, time cap negative, and then you go over here and erase that? That's what you would have done? You would have been wrong. You need the negative there. Why does it make sense to keep that negative? Why are you not bothered by it? You have an idea?
If you take the ln of that fraction, you would get a negative number. And the number cancel that.
You ln of 1 over 200?
Yeah.
How would you look at that?
Like if you actually like plug that into the calculator, would you get a negative number?
You would get a negative number. One, you can do what we did, same maneuver with ln of a half. You can realize that this is ln of 1 minus ln of 200. ln of 1 is 0, so this is really negative ln of 200. So you could have written this as 30 times ln of 200 over ln of 2. You could also remember that, well, ln looks like this. It passes through 1. So if your input is less than 1, so it's like over here, 1 over 200, the output will be a negative number. And so this is negative, so it multiplies by a negative, it makes it positive. So this is actually the answer. In a couple of ways you can see that. So that actually makes sense. So don't try to be slick and erase a negative sign. In this case, it's supposed to be there. But it is something you should be considering. You should always consider whether or not your answer makes sense. So that's how long for it to have 1 milligram. E. What is the rate of growth at the time there is 1 milligram remaining? Is rate of growth when there's 1 milligram remaining? What is that asking for? P prime. I know that P prime is equal to minus RP because it's exponential decay. So what do I just plug these in now? R I know is ln 2 over 30. My P is 1. So that's the rate of growth. It's decreasing at a rate of ln 2 over 30 milligrams per year. And that's kind of this question. By the way, these kinds of calculations are the kinds of calculations we use in like carbon dating, for example. So we can measure the fact that carbon 12 is radioactive and it does decrease over time.
14.
You can measure it, carbon 14, you can measure it over 2 periods of time. and sort of see how it's decreasing. And then you can come up with the R, and then you can figure out the half-life is, what was it? What's the half-life of carbon-14?
About 5,600 years.
It's 5,000 something, I never remember the number. 5120 or 5,000 something. But then you can if you dig up a fossil or something and you measure the amount of carbon-12 in it, and you know, oh, there was this many grams of carbon-12, we expect this living animal to have this many grams of carbon-12, so then you can backdate how long it would have taken for there to be this much grams remaining, which is this kind of problem. That's sort of how carbon dating works. Very naive way to look at it, but that's basically it. Let's move on to example 3. So in example 3, we're talking about money being compounded continuously. So here we see the phrase compounded continuously. That basically means exponential growth. How do you guys define a mole from like chemistry?
Mole is 6.02 times 10 to the 23 if anything.
Okay. And you know where that standard came from? Like how they came up with that?
Avogadro. Some dude with
Yeah.
It's Avogadro's number, but where did it come from?
This guy Avogadro did a bunch of calculations.
It sounds like an avocado. That's all
I know that we were told how we, but I'm not sure.
We also know that a mole of gas occupies 22.4 liters.
At
STP.
standard STP.
273 degrees Kelvin. 1 atmosphere of pressure.
I think that's where carbon-12 came in. A mole was really.
Carbon 14.
No, it's not carbon-12.
Carbon 14.
Carbon-14 is the isotope. It decays into carbon-12.
Yeah, and it's like 1%.
Yeah, but isn't a mole there like how many grams of they measure the amount of particles in carbon?
Yeah, well,
12?
carbon
And then they came
naturally,
with, let's call that a mole. And
Carbon naturally
it happens
has,
to be Avogadro.
3 isotopes that are the most
Yeah,
common
carbon
is
is all over the place.
carbon 12, there's carbon 13, carbon 14 is the one that's really, really small, and my chem professor tried to tell me that carbon 14 didn't exist, and I was like, but no, you're wrong.
So Beatrice is very passionate about carbon. If I ever
I-
get Beatrice
yeah,
to talk up,
okay.
let's talk about carbon. Let me tell you about carbon, okay? Carbon 14. That's
Jhevon,
where it's.
you know what they say? You can't trust atoms. They make up everything.
Yeah. You know? She's like the spokesperson for carbon 14.
I like carbon, okay?
It's carbon 14. Like everything likes carbon. Like literally, almost pretty much
Literally
everything. Everything likes carbon.
We're made out of
Okay.
carbon.
Okay. So, so now we have this fake bank that's actually giving us 5% interest compounded continuously. You can't even get that compounded yearly from any bank today. You like 0.1%. Well, let's imagine we have a bank that's giving us 5% interest compounded continuously, and suppose we deposit $4,000. So A. Write down the differential equation together with the initial condition. So what does that mean? What's the differential equation? The P prime equation, differential equation. This refers to the phi prime equals RP. We know it's exponential growth, so it's positive. With initial condition, what equation is that? That's actually an equation as well. Which one is it? That's the equation that tells you the P naught value. So P of 0 equals whatever that is. So this, in this case here, it's P prime equals, what is R? In this case.
Is it the 5%?
It's the 5%, but you write it as a decimal, so it'll be what? 0.05 times P, and that's your differential equation. And your initial condition says that at time equals 0, what is your amount? 4,000. So this is the differential equation with the initial condition. At what rate in dollars per year is your account increasing when the balance reaches 6,000? So we want the rate of increase at P equals 6,000. What are we referring to? P prime. So we just want P prime. We know that equals RP, and we just plug it in. R we know is 0.05. P we just were told is 6,000. And that's the rate at which it's increasing when it's 6,000. How long will it take for your principal to reach 5,000? So you deposit 4,000. How long before you have 5,000? How long before your money, the interest adds $1,000 to your money? Another very common question to ask here is, how long before you double your money? That's also something I could have asked, in which case you'd use the time doubling equation. But how long before you have 5,000? What are we looking for? Right, how long means we're looking for time. How do we get to it? What equation do we use? What equation to solve for time?
So PT equals P0 or no?
Right, the PERD formula. P equals P naught E to the RT. We can plug these guys in, so this is, I want the current amount to be 5,000. I started with 4,000. And my R I know is 5%. And I want to know what T value will allow this to happen. So T is what I'm going to solve for. I'm going to divide both sides by 4,000. This gives us 5 over 4 is equal to E to the 0.05 T. ln both sides. Well, this side cancels. So I get ln of 5 over 4 equals 0.05 T. And so this is ln of 5 over 4 divided by 0.05. 5 over 4 is inside the ln, you cannot touch it or mess with it, but that's going to be your answer. So that's how many years before you can get to 5,000. And we'll stop there. So, as I mentioned in the other class, I hired a special counsel to investigate the soy boy incident, and we had new evidence now, so I'm going to get the testimony. So, soy boy who knows who he is, we're tracking down on him.
Or she.
Oh no, we're pretty sure the evidence is pointing to one individual, but due process must be upheld. So when we get back, we have test 2, and this is not on the test, I don't think. Right? So the homework for this will be due like the day after the test. But we'll stop there. The test, I believe, is up to marginal analysis, which we covered last time. The review for that is posted, and I will see you guys when you get back.
I have a class tomorrow, but I don't
Yeah,
have
where
class.
does it